All right, our quick look at the calendar, and we got to pay attention to the calendar today because there's going to be a change in the calendar from what you have been handed out. So today is exactly what it says. We're going to do derivatives of exponential functions. Here's the change. I cannot be here on Friday. Class is not canceled, and I suspect many of you are here anyway from your 8 o'clock physics class. But what's going to happen Friday is the project check-in day. So this coming Friday, you're going to be working with each other, and the reason I wanted to switch those days is because on the first project check-in day, I feel like there was a lot of really great collaboration that was happening, and I hardly did anything over here on the side. So if I can't be here on one day, then it seems like making that day the project check-in day is the best one to do. But actually, Caitlin on that day is going to be next door in her class, but she will poke her head in when she's able and tackle any questions that that we have. Okay. So project check-in day is coming up this coming Friday. And then when we come back from the weekend, I'll be back on Monday, and then we'll do the trig functions day. All right? So we're just switching 2 days. One thing that we are not switching is this quiz that's coming up. It's scheduled for Monday. It's still scheduled for Monday. It's a take-home just like before, so I will hand you a take-home quiz on Monday. Okay? Any questions on the new calendar? Just switching the 2 days, but the quiz stays just where it is. Okay, then let's start on page 18. Before we do, let me give you guys like 60 seconds right now. This is something Caitlin did first time around with the projects. Since we're coming back on Friday and working on the projects, it might be a good idea to come to some consensus with the people at your table. It says we're all going to get to this point on the project by Friday, or this point on both projects by Friday. So make some kind of plan. It could be that some of you haven't started, could be some of you are far in, but talk to each other for 60 seconds and make some plan for where you're going to start working together on Friday. 18, and we'll start at the top of page 18. Can we go to Andy for the daily summary?
Daily summary. Today we discover formulas for the derivatives of exponential functions. Use them with other derivative rules to solve optimization problems.
You know what, like after you graduate, your job is going to be like town crier for like any kind of event where there's like a parade and somebody at the front who's just like ringing a bell and shouting. That's it.
Like, today, free pancakes. Giving out free pancakes on Saturday.
Okay, let's go to number 1. Number 1. Okay, here we go. Come on back. Can we apply the power rule to find the derivative of e to the x? So don't write this because it's wrong, but x comes down, copy the stuff, subtract 1 from the power, right? What's wrong with this? It's not right at all. That's true. Yeah, so like if it were x to the 5th, then we could do it. If the variable's downstairs and there's a constant sitting upstairs, then that's our power rule, 5x to the 4. But this is a completely different creature, this e to the x. So it's a completely different rule. And I think some of you already know what the rule is from the reading, and we kind of hinted at it in a previous class. But we looked at some tangent lines for the e to the x function, and I'll pull up a sketchpad version of that. So taking a look at this picture, there's a massive dot at the point 0, 1. And then there's the tangent line that's drawn in, and the slope of the tangent line is right there at 1. And we're just going to observe that the y-coordinate at the point happens to be the same as the slope of the tangent line at this moment, right? And then we're going to take that massive dot and we're going to move it to the right. What's going to happen to the tangent line when I move this point to the right? It's going to be steeper. So we're going to move to the right and it's going to get close to there. And so the tangent line is steeper and the point is also higher than it was before. And what do you notice about the y-coordinate and the slope? They're the same. And so it's crazy, but it's true. Whatever the y-coordinate is of the point, it's exactly the same as the slope at that point, and it works even if we go negative. So here the y-coordinate, so the x is like -1, the y-coordinate is this, and the slope is that. And then if I keep going left, what's kind of the limiting value to these slopes? 0. Will I ever get to a perfectly horizontal tangent line? No. And does the curve ever get to the x-axis? No. And so it's working surprisingly so that the slope is the same as the y-coordinate. So here's our new derivative rule, number 4. It says the derivative of e to the x is e to the x. Great. Which means that we're going to add in here another chain rule thing. We're going to write a rule for the derivative of e to the stuff. Okay, so we treat it like normal. So what's the first thing we write for the derivative of e to the stuff? It's just e to the stuff, because it behaves just like e to the x. But then we pay for it. The chain rule says, let's say plus, minus, times the derivative of the stuff. That's what the chain rule says, right? So you treat it like normal, and then multiply by the derivative of the stuff. And then coming down to number 5, same idea here, but instead of the derivative of e to the x, we're looking at any number to the x, like 2 to the x or 17 to the x. So it turns out that the derivative of a to the x, where a is a constant, is a to the x. That part actually seems reasonable, right? E to the x is e to the x, a to the x is a to the x. Unfortunately, we have to multiply by ln of a in the more general case. What happens if we try to use this bottom formula here applied to e to the x? So you change the a to an e. Then this would say ln of e, which is 1. So actually this bottom rule is really the rule. The e to the x is just a special case where you don't have to stick on the ln part because it happens to just be 1. Okay, so let's see if we can use our 2 new rules. We can also throw in here the chain rule version of this. Let's write this in. Derivative of a to the stuff is what we're after. So we treat it like the normal rule, which we've just learned. So what's the normal rule say here? Times ln of a. That's the normal rule, right? You just got to stick on that ln of a anytime it's an a. But then the chain rule comes in and says, hey, also what? Multiply by derivative of the stuff. Okay, so let's see these 2 rules in action here with number 6. So we're trying to find the derivative of that whole thing, 4e to the x plus 6 to the x plus x to the 6th. So here we go, equals. Okay, that 4e to the x. You could use the product rule, but you don't need to, because 4 is just a constant. And so when you have a constant multiple, does it stay or disappear? It stays. So the 4 is just hanging out waiting for you to take the derivative of whatever is sitting there. What's the derivative of e to the x? E to the x. So there you go. Derivative of 4e to the x is just 4e to the x. Plus, pluses are nice when you take derivatives. Okay, now we have 6 to the x, which is an example of a to the x. So what's the derivative of 6 to the x? That's it, 6 to the x ln of 6. And I'll put a little dot for times just so we're really clear. It's a multiply. Okay, and then one more plus, and then the derivative of x to the 6th, 6x to the 5th. So we really have to start being aware of these like kind of subtle details. X to the 6th and 6 to the x, they sound the same, they almost look the same, but you got to be really clear because their derivative rules are quite different from each other. One last thing I didn't ask for in the packet, but I'm going to add here is let's find the second derivative of that original thing. So we're just going to find one more derivative. Okay, so now we're working off of purple, which is the first derivative. So we're just going to take the derivative of purple. What's the derivative of 4e to the x? It's 4e to the x, it doesn't change. Plus. Okay, now we've got this 6 to the x times ln of 6. So first of all, the ln of 6 is a constant. And constant multiples do what when you take derivatives? They stay. So I'm gonna bring the ln of 6 to the front just so that I don't forget about it. And now we're trying to take the derivative of this piece. We've already copied the ln of 6. So over here, I need to put the derivative of 6 to the x. What is it? That's it, right? That's our a to the x rule. Yeah, and then we're going to smush the ln of 6's together in just a second. Everybody see that? Like it can look confusing because there's two different ln of 6's there, and they're there for different reasons. And derivative of 6x to the fifth is 30x to the 4. Good. And so then we'll take Andy's suggestion just to rewrite this piece. 6 to the x, ln of 6 squared. Questions on that? Okay, so the activities start on the next page, but there's the activities are kind of in two parts, and I want to get you through the first part rather quickly. So I'm going to ask you to skip numbers 1, 2, and 4. So the very first two problems on this page you're going to skip, as well as number 4, because my goal is to get you to this thing called the surge function. So on the very next page, can you guys go to the next page where it has this surge business in the middle? So you are going to read this part, the paragraph right above the graphs. But you are then temporarily at least going to skip number 1, okay? There's a ton of questions about these graphs on the pages after, but I want you to skip number 1. And if you get through everything else, then you come back to the ones you skipped. Okay, raise a flag if I can help.